And I'll go ahead and start recording now. So here's our notes from yesterday. We left off, kind of rushed a little bit at the end. I did want to do some extra practice graphing. And we left off with the distance formula and some practice sketching. So let's pick up there and then we'll get into vectors. Vectors are fairly simple once you practice using them. So I'm going to go ahead and say, practice these, sketching some of these surfaces on your own. We'll get into functions here soon as well. And once we get into functions of multivariables, it's going to be even more practice sketching, especially with you guys being the honor section, being engineers. Sketching, I know it sucks for some of you guys that aren't artistically talented or aren't like visually, spatially coordinated, but very good practice for the fields you're getting into. Unless you're if you're strict computer science, maybe not so much, but pretty much any other field of engineering, civil, mechanical, aerospace, all of those, you're going to want to be able to draw and have a visual representation of the systems and objects and projects you're working on. Okay, let me get some blank paper here. So distance formula, I did want to go over a couple examples that were in the notes. That the distance between 2 points is pretty easy to write down. So our standard distance formula is the Pythagorean theorem, now in 3 dimensions, and we can generalize that to higher dimensions if we want. And it's pretty easy. If I give you 2 points, plug in the numbers. We've got 1 point, x1, y1, z1. The other point given by coordinates x2, y2, z2. We just take the difference in x squared plus the difference in y squared plus the difference in z squared and square root everything. But throughout the semester, we're going to see a lot of distance equations or different distance problems where we want to minimize distance or calculate the distance between different geometric objects. So getting a sense of how distance is measured is something we're going to be building up on. And on Friday's lecture, we'll talk about the dot product, which will make some of that a little simpler for us once we introduce vectors as well. So some of the problems I wanted to look at from the notes were find the distance from the point 1, 3 minus 2 to the xy plane. So visually, again, if we want to plot this point, let's see if we can go ahead and do that. We want to go 1 on the x, 3 on the y, and then down 2 on our z-axis. So our point's going to be about here. I'm going to go ahead and let's use some red to draw our little guide marks. Doing this a little quickly. So here's our point 1, 3 minus 2. And notice that if we want to find the distance to the xy plane, well, the distance between any two objects, as soon as we start talking about more complicated geometric objects, whether it's planes, whether it's some type of surface, usually when we say the distance between an object, it's going to mean the shortest distance. So when we say the distance from a point to a plane, we mean the direct shortest distance between those two objects. So the distance from our point and the shortest distance to the plane. We'll, excuse me, we'll expand upon this a little bit more once we get into our notion of a dot product. But the shortest distance, maybe if you've learned in a previous geometry class, that the shortest distance between a point and a plane is going to be a perpendicular. So in our XY plane here, we want to walk from that point directly perpendicular so that we have our shortest path and hit the XY plane. Well, if we walk directly perpendicular to it, the point we hit is just going to have the same X and Y coordinates. Since those aren't going to change, we're going to walk orthogonal or perpendicular to the XY plane, means we're going to be walking straight up and down in our Z direction. So our Z coordinate is just going to be 0. So once we have the point on the object we're hitting, now I can just find the distance between those 2 points. So our change in X is 0. Our change in Y is 0. And then how far did we have to walk in our Z direction? I guess we have to decide which point we started and ended at. Let's say if we ended here, if we ended at our plane, we'll do 0 minus our -2. Of course, that's going to be squared. And so we'll get square root of 4, where the distance is just 2. In other words, another way of thinking about this is if we want to project a point or project the coordinates of a point onto the plane, well, when we're projecting, we think of an orthogonal projection, meaning we're shining a light in the Z direction perpendicular to the XY plane. And where are we going to land? Well, we'll keep the X and Y coordinates. Our Z coordinate will be 0. And of course, how far did we have to walk to change that Z coordinate? Well, we just walked a distance of 2. If we change our situation now a little bit and say, find the distance from 1, 3 minus 2 to the Z axis, I'm going to go ahead and use the same picture since we've got one drawn. Let's see if I have a different color. Not handy. I'll go ahead and use green then. So if we want to walk to the Z axis, our point is going to project at the same level. So if we want to walk from our point here to the Z axis, we want to walk the shortest distance. It's going to be a straight line from our point to the Z axis. Well, what's changing if we're going to walk on this direction? Well, the Z coordinate is going to stay exactly the same. We don't want to walk up and down on the Z axis. That would just increase the distance that we're walking. However, what are we changing? We're actually going to change the X and Y coordinates now. So if we're going to hit the Z axis, our X and Y coordinates are both going to be 0. The Z coordinate stays the same. So we have to use a little bit of geometric spatial reasoning in both situations to understand, well, what point are we hitting? As soon as we have that information, now we can just, again, plug that into our distance formula. And so notice that the distance in this case is going to be our change in X plus the change in Y squared. And then our change in Z now didn't actually change. So we, in some sense, have reduced our distance formula to a 2-dimensional distance formula. Since we are restricted into this plane at Z equals -2, really all we're doing now, it's basically the Pythagorean theorem on the X and the Y coordinate. So we've got our change in X squared plus change in Y squared. So what do we get in this case? We've got 1 plus 9. So we'll get square root of 10. Okay, and then the last example I wanted to do from the notes was to practice some of the sketching and traces. I don't think we went over traces very well on Monday. So we want to find the equation of the surface whose points are equidistant from both the xy plane and the z-axis. So this one's a little tricky, going to be a little bit more involved, especially with this introductory material. We're using this description in words, and then we have this notion of the distance formula. Now we actually want to be able to come up with a closed form expression, an equation that relates all of our variables to define this surface. Then we want to practice sketching it. So how do we come up with this equation? So let's let our surface, it's going to be the set of all x, y, and z that satisfy our conditions. I'm just going to write it out as conditions. So we have x, y, z coordinates, and they're going to satisfy these distance conditions. Well, what are those conditions on these x, y, and z? What's that going to be? So based on our previous example, we know that the distance to the xy plane is going to be the square root of our any point. So we're picking some arbitrary point x, y, and z on our surface. Well, what's the distance from that to the xy plane? As we saw in our last coordinate, it's going to be, our last example. This. Meaning that the point on the xy plane that we hit is going to be xy 0. So our change in x is 0, our change in y is going to be 0, and then we are simply going a distance of z to hit the xy plane. Likewise, the distance to the z-axis, well, if I have a point xyz on this surface and then walk to the z-axis, what point are we going to hit? We're going to hit 0, 0, z. In other words, our change in x is going to be x. Our change in y is going to be y. And the change in z stays within that plane. So it's going to be 0. So we know that by our conditions, both of these distances have to be equal. And that's going to define our surface. So our equation is going to be z is square root of x squared plus y squared. Okay, so how do we sketch this? What we want to do is pick traces. So So let's pick some from z. So at z equals 0, we get the equation 0 is equal to the square root of x squared plus y squared. Well, what does that mean? This is going to imply that both x and y have to be 0. So this will reduce to x squared plus y squared equals 0. The only way a sum of two squares is 0 is if both of those numbers themselves are 0, which means the only thing we have is this point. If we pick different values of z, let's say z equals 1, we get a circle of radius 1. And likewise, as we can kind of see what's happening here every time I pick a value of z, let's pick z equals 4. No, sorry, let's pick z equals 2. So we pick z equals 2. 2 is square root of x squared plus y squared. And then when we square it, we'll get 4 equals x squared plus y squared. In other words, we're getting a circle now of radius 2. Let's do a couple more for the x and y coordinates. So if we pick, say, something like x equals 0, setting a coordinate equal to 0 when you can is often really nice, because then that's going to project it onto that given plane. So x equals 0 is going to be our YZ plane. And then we can see what this object is going to look like on the YZ plane. So we will get z is equal to square root of y squared, which is going to reduce to z is equal to plus or minus y. Another way of looking at this is z. This is another way of writing z as absolute value of y. And likewise, if we choose y equals 0, we'll get z is square root of x squared, which is absolute value of x. And so z is plus or minus x. So what is this object going to look like? The traces in this regard. So on our x equals 0, we're going to have our yz plane. We get absolute value of y. And here we're going to get absolute value of x. And I missed one thing. I was thinking about why I missed this. Let's go back 1 second. I missed a plus or minus on this coordinate. So this is going to be square root of z squared, which gives us a plus or minus z here, which is good because we need a plus or minus z here. Another way of writing this equation, if we just want to square both sides now, so this is saying that z can be positive or negative. As I had it, I only had the positive version of it. I forgot that extra minus sign. And so if we square both sides, that will account for z being allowed to be both positive or negative. So another equation that we really like with this is z squared is x squared plus y squared. So these equations aren't going to change. If I plug in 1 for z or 2 for z, we'll end up getting the same equations for a circle. The only thing that is going to change is these guys here. So since z should be plus or minus, it'll give us plus or minus the square root. So not only do we have the square root, but we also have the negative square root. So it's really these two intersecting lines, z equals x, z equals negative x, z equals y, z equals negative y. And so when we want to graph this in 3D coordinates, what's it going to look like? Hopefully everyone can see that as we saw our vertical levels, so if I'm slicing this thing horizontally as we increase, what did it look like? We had circles. And as z increases, that circle is getting bigger. How much bigger? Well, if I look at a cross section on the zy plane, it should just look like two lines. So as you can kind of imagine now, if we just take these and have our circles, it's going to look like a cone, a two-sided cone. So our object, let me go ahead and use a different color. Is going to be our cone. Any questions on that? Everyone see it? So practice more of these, and we'll practice in the coming weeks. As I mentioned, visualizing, sketching is going to be really important in this class. So the sooner you just start working with these different equations and trying to make sense of the different equations and what types of objects they make, it'll really help in the future. And we'll do more of this once we get to 10.6. Okay, so let's move on to vectors. So you guys watched the preview assignment. So what is a vector? Vectors are mathematical objects with a size, which we call the magnitude, and direction. Can anyone give me examples? What are some examples of vectors that we can use in the real world?
Force, motion, acceleration.
Yeah, so forces, motion, yeah, so specifically acceleration. Velocity is another good one. And you hear these all the time. These come up in like the news and sports. People will talk about vectors, but like, of course, being real world situations and whatever games or things that we're playing or however we see them, people don't often describe them as vectors. So anytime if you hear anything about a golf tournament, golf and big thing, you got to know the wind direction, right? Anytime they say the wind is blowing north-northwest at 12 miles an hour, 12 miles an hour is our magnitude, and the direction is the north by northwest. If you are driving 60 miles an hour on I-70 West, you have a direction. You're traveling west, and your magnitude, the velocity you're traveling, the magnitude of your vector is 60 miles an hour. If you are pushing an object in a certain direction, So if you are lifting a weight up off the ground, you are applying a specific force to lift that weight. In the direction you are applying that force is, or will at least have, a vertical component. You are lifting it straight up off the ground. Or if you're lifting it at an angle, there's a direction you're applying the force to get that object to move. So a collection of vectors called a vector space satisfies two operations. Scalar multiplication and vector addition. So you'll study vector spaces a lot more in generality in your next class. So after you all do super well and get A's in Calc 3, you're going to move on to linear algebra and differential equations. And linear algebra is the study of specifically these mathematical spaces called vector spaces. So for now, just for this class, we want to just introduce you to some of the basic operations, namely scalar multiplication and vector addition. What does this mean? This means that for any vector, we can multiply it by a scalar. And what do we mean by a scalar? Just a number, a real number. So this stretches the vector and it will change the direction if negative. So just geometrically, what's going on here? If we have some vector here that I'll call vector A. So vectors we denote with arrows, the arrow indicating the direction and usually the length of the arrow indicating the magnitude. So if I want to draw the vector 2A, it's going to take the vector A and it's only, I guess we should say, to be a little more specific, let's not say change the direction, but flip the direction. So just going in the exact opposite direction. Multiplying by a scalar number is only going to keep us on the same line that vector is pointing in. So it's either going to stretch it along that line or shrink it if we're multiplying by a fraction, or flip it and point it in the opposite direction. It's not going to rotate or anything like that. So 2A is just going to be the same direction, but twice as long. If we say something like -1/2 A, still in the same direction. So I'm trying to make all of these parallel here, but half as long. And then vector addition. Geometrically just means that if I have any two vectors, let's say this is vector A and this little one here is vector B, then how do we form A plus B? You want to think of just drawing the parallelogram. So when we say vector addition, it is a commutative operation. So I can take a vector A, I can add on a vector B, And that's going to be the same thing as starting with vector B and then adding on vector A. It doesn't matter the order. So we should always end up at the same place, whether I go A and then add B. So another way we describe this is by moving it tip to tail. So if we start with vector A and then add vector B, we just want to start at the tip of A and then walk in the direction of B. Or I can start with at the end of vector B and walk in the direction of A. We will end up at the same point, and the net result is going to be the vector as if we started at that same origin and then walked directly to that point. So that's going to be A plus B. So geometrically, that's what's going on. I'll leave it to you guys to check the notes. If we need to do A minus B, hopefully you can interpret that as just vector A plus negative of vector B. So take a look at the notes, draw some diagrams, and work that out of how to draw, how the diagrams work out with subtraction of two vectors. Okay, so let's talk about vector components. So far we've just kind of drawn abstract vectors, drawn arrows, but typically wherever we draw vectors, we like to think of it as of a coordinate frame centered at the base of the vector, meaning that wherever we draw a vector, we can draw a coordinate frame right at the base. And relative to this coordinate frame, well, we have an X direction, a Y direction, and in 3 dimensions, we'll have X, Y, and Z. And so what we can do is describe the vector similar to how we were doing our points in 3-dimension or 2-dimensional space. We think of it as having components. So for example, if I describe a vector V, instead of using rounded brackets like we do with points, we just use angle brackets. So if I say we have a vector that is 4, 3, that just means its x component, or the projection on the x-axis, is a length of 4. The vertical component is a length of 3. And so this would be our vector V here. In terms of the length or magnitude, we describe that by these double lines. So it's like an absolute value, but we kind of like double the absolute value, just to be indicative that we are taking the length of a vector. It's the size of a vector. Just like the absolute value of a number is the size of the number, the distance it is from the origin. In 3 dimensions or higher, the length of a vector, or the magnitude of a vector, is just the length of the vector, or the distance the tip of the vector is from the origin. So in this case, it just follows our standard Pythagorean theorem. So, 4 squared plus 3 squared square rooted, going to give us 5 squared in this case. In 3 dimensions, let's pick some easy numbers and see if we can draw this. I'll use my Radigan to draw some guidelines. Let's say we have a vector, let's call it U, another common letter for vectors. And of course, if you haven't picked up, we draw the little arrow on top to indicate that the object we're talking about is a vector. In components, let's say it's 2, 1, and 3 up on the z-axis. So we go 2 on the x, 1 on the y, and again, just like drawing our points, you kind of got to draw your boxes, because the place the tip ends up is going to look a little weird. So here, I'll draw it in green. So starting at the origin out to that red dot is going to be our vector u. And just like finding the magnitude of points, or the distance a point is from the origin, our magnitude of u follows our Pythagorean theorem. So let's see, whatever that is, 4 plus 1 plus 9, root 14. So given, sorry, let's talk about our standard unit vectors first, and just unit vectors in general, unit vectors in general. So standard unit vectors for notation, instead of the arrow on top, we'll put this little hat, is what we call this. So I hat is just the unit vector that points 1 in the x direction. Our j hat points 1 in the y direction, and k hat points 1 in the z direction. So if we were to draw our coordinate frame, that's our I hat, that's our j hat, and then our k hat is the vertical one. So commonly when we have these vectors in component forms, I like to use the bracket, angle bracket notation. I think it's a little more concise, though sometimes it can be a little redundant. If we can write a vector, let's say we have another vector v, and let's write it in component form as 5, -5, -1, and 7. We often write it as -5 I hat plus, or just straight -1 j hat plus 7 k hat. So this one's a little more to write. It does kind of come in handy if we have a vector that has like zeros in it. So for example, if you have a vector that's, let's say 10, 0, and -2, when we write that in terms of our standard unit vectors, we can write that as just 10i minus 2k. So sometimes it's a little quicker if one of the coordinates is 0. And I would also say be careful with that if one of the components is 0. If you're going back and forth between component form, don't forget that dimension. So again, this just comes down to our fact of scalar multiplication. Each of these I, j's, and k's are vectors in and of themselves, and we can scalar multiply those vectors by numbers, whether positive or negative. So of course, this component, if we want to call it the x component, or the component in the x direction, we were talking about the length of that vector, or the quantity of that vector in the x direction. So we would have a -5 in that regard. If we are given 2 points, let's say A. So often when we write points, sometimes we write like give a point a letter and say A equals. Sometimes they just write it as like A and then put the components. So you know we're going to have points if it's rounded brackets. We say that the vector AB and we'll put our little vector line over it, points from A to B. And this will come in handy once we get into lines. It is the vector, whereas if I start at point A and walk to point B, it is the resultant vector, or what we call the displacement vector. It encodes the direction we walk, starting from A and ending at B, as well as the distance. So the way we do that is just do B minus A. So we do B minus A, 2 minus 1, 8 minus 2, and then 5 minus 2. So this is going to be our displacement vector. If we had a problem that says find the unit vector from A to B, we simply divide by the magnitude. So given any vector, we can do this. If we want to modify our AB and make it a unit vector, in other words, put a hat over it, we just take the vector we start with and divide by the magnitude. So we can scalar multiply. Be careful with division. We cannot divide two vectors. However, I can take a vector and multiply it by a scalar. In other words, multiply by the reciprocal of the magnitude. So all we have to do is find the magnitude. Here, let's do it in parts. Magnitude of AB is square root of 1 plus 36 plus 9, which is going to be square root of 46. And I don't know if we can simplify that root anymore. I'll leave that to you guys if we can. So our AB hat is just going to be, let's write it first as 1 over square root of 46 times our vector 1, 6, 3, which if you want to simplify it, oftentimes I do think it's better to leave the scalars outside of the vector, especially to simplify some of the arithmetic you got to do. But to find the proper components, you would just divide each component by root 46. Any questions so far? So all pretty basic. Take a look over. There's an example in the book. I'll just draw it real quick since we only got 5 minutes. I'll leave it to you guys to take a look at it. It's basic use of trig, but if I have a vector v, or perhaps I know the magnitude of the vector. Oops, sorry, let me get that on screen. Suppose we know the magnitude of vector v, and maybe I have some information about the angle. We want to express the vector v in component form. In other words, the components are going to be functions of the angle. So take a look at that. I'll give you a hint. You're going to want to use sine and cosine, but it should be pretty easy to figure out. Let's do one more example, or at least get it started. We only got a few minutes here, so we can get it started. And this will be an important example that comes up in physics. And as was mentioned at the beginning of class, we often see forces as vectors. So a lot of introduction to physics classes when you're looking at statics, Suppose we have a mass being suspended by two strings. And we know that the weight of the mass is 75 newtons. Well, the object isn't going anywhere. So by Newton's law, all the forces have to be balanced. Force is equal to mass times acceleration. So if it's not moving, if it's not accelerating, all the forces, the sum of all the forces on this object have to be zero. And so what we want to do is find F1. I think is what's listed in the notes. We could also find F2 in this process. In other words, what do we want? We want expressions involving, or a component form of F1 and maybe F2. So how do we do this? So we know that, let's go ahead and draw our reference frame at this knot here. So the direction of the forces, F1 is going to point in this direction along the tension of the rope. Likewise, F2 is going to point along the direction of its rope. And then the weight is hanging straight down. And so that force is going to be straight down. This tells us that we can come up with equations. We know that F1 plus F2 plus our 75 newtons. However, this 75 newtons we need to express as a vector. How do we express it as a vector? Well, it is relative to our coordinate frame pointing straight up and down. We just have two-dimensional vectors, so let's just use x and y. So our y is going to be our straight up and down. So this is actually going to be a negative j hat component. But that's not going to give us, oh, sorry, this should equal 0. All the forces should be balanced. And specifically, let's actually be specific that our 0 is the 0 vector. So 0 in each component. So that's one equation that's going to help us out, but we need a little bit more. We're going to have to take into account these angles here. So because the direction of the force points along this angle here, we can actually figure out the components of F1 and F2. So it's a pi over 3. We know that relative to this coordinate frame, we can actually fill in our other angles. This can be pi over 6. So the magnitude of F1 in components will give us the length. And then how do we use this magnitude to find the components? I'll give you a hint. It kind of came from this last problem that we skipped over. But if we wanted to break this down, let's draw the vector a little bit bigger here. It will be in this direction along the rope. And then just to give ourselves some space on the red, we will have an x component and then a y component. So be careful of which angle you use. Either one will work. Let's go ahead and use this pi over 6. I think that's a little different than the one than how it's done in the notes. But if this pi over 6 angle is here, then our vertical component is going to be cosine of pi over 6. So the magnitude of F1 times cosine of pi over 6. The horizontal component then is going to be the magnitude of F1 sine of pi over 6. But we got to be careful about this. So since this is kind of a real world model that we're coming up with, the relative to our coordinate frame, this x component of F1 is negative. And so since we're using angles that are less than 90 degrees, it's going to give us a positive value. So let's go ahead and throw in a minus sign there. Likewise, so sorry, I'm a little bit late. Let's go ahead and write down F2. So we'll have magnitude of F2. Unfortunately, we've got a pi over 5. So this angle here may not be good to use since it's going to be 90 degrees. We can go ahead and say that our horizontal component, so if this one's going to be pi over 5, the other thing we can do is take a look at this angle here. So by geometry, it'll be the same as pi over 5. So our x component will give us cosine of pi over 5 times the magnitude. Y component, magnitude times sine of pi over 5. So using this equation here and these values, when we actually look at our component form, I should be able to add the x components, and that should equate to 0. So again, our 0 vector is just zeros in all coordinates, and two vectors are going to be equal, or a vector equation is going to be satisfied when each of the components are equal. Meaning if I take my x component from f1, x component plus of f2, there's no x component here, so it should equal 0. So the sum of these two values should equal 0. Then our second equation, we should have the sum of this value plus this value minus 75 is going to equal 0. So set up your systems of equations. We've got two unknowns now, just the magnitude of the vectors. And then you can solve everything else. Any questions?